Okay, good evening. I have still written on the blackboard what we have seen last week because it's good to refresh your memory. But in fact, it's completely independent of what we are doing today. But still, since I did it all the time, I just do it also today. So what I did, we discussed networks and application of networks. So networks is an oriented graph. And I define what is the in at one vertex and what is the out at one vertex. It's quite natural, the incoming row, the outgoing one, and also the set of edges between A and B. So having one endpoint at A and the second endpoint at B. Then I introduce ST network, which has network with two specific vertices. So you fix one, you call one S and one T. Like for tree, we have also the notion of rooted tree. And on such a ST network, I put a function which is a capacity. It's a maximal function in a certain sense. I also define what is a flow, which is, you have more condition on a flow because at every vertex, the sum should be 0, but it also upper bounded by the capacity. And then I define what is a cut. It's a partition of the graph with S in U and T in U complement. And whenever you have a flow, you can define its value by a certain formula. And we have seen that this value of the flow is independent of the cut we choose. And it's always smaller than a certain number, again, for all cut. So I have defined this last week. So it means since these quantities are upper bounded, you can look for maximal flow, which gives you a maximum value for this. And you can also look for minimal cut, which gives you the minimum value of this. Since the number of cut is finite, the minimum cut always exists. For the maximal flow, you have to be a little bit careful. It exists if the values are rational. It might not exist if it is real. And okay, this is still the definition. It turns out that the value of the maximal flow is always smaller than this function at the minimal cut. And in order to find what is this maximal flow, we introduce the notion of ST pass and ST quasi-pass, and then an algorithm for finding a maximal flow, how to increase the flow step by step. And it turns out that if you put the capacity equal to 1 everywhere, the maximal flow gives you the maximum number or the number of edge disjoint ST pass, so the number of paths with different edges from S to T. And then we have seen applications. The applications are quite natural and they were quite easy to understand, and you just take these examples and rephrase them with what we have seen before, and you can find the solution. And the solution essentially consists in exhibiting the maximal flow. All right? So this is what we have done last week. Today, we start with random graphs, because random graphs have many applications, and it's quite natural. So this is chapter 10, random graph. And today we study one model, which is called this GNP model. I will introduce it. I'm sure you are familiar with this notation, but I just remind you, you know what is n factorial? I'm sure all of you know. You also know the binomial coefficient. So if I pick you, you know that this is p factorial over q factorial, p minus q factorial. And in particular, I will need today n2, which is n times n minus 1 over 2. It will appear at many places. Okay. 10.1 about basic results. So you have to know that this model has been introduced by 3 persons. The GNP, it was introduced by, I write the name because they are quite rather famous, introduced by Gilbert Elbers and Rennie. Already about 60 years ago or 70 years ago. And oh, it's an I and not a Y. Okay. YI. Okay. So, okay. Sorry. So in my notes, it's probably not. Okay. This model has different names. I wrote these different names in the notes. What is the N and what is the P? Yes, N in the model is going to be the number of vertices. And P, so it means in particular, this is an integer. N is an integer, it's not 0. And P is a number between 0 and 1, is a probability of existence of an edge. And this probability is the same for all edges in the graph. So the probability of existence of edge. So I just give you an example. We have 6 vertices. So this graph is going to belong to G6 and let's say 1/2. So I can draw a few edges. Be careful. So what is the maximum number of edges for 6 vertices? It is?
Here's 2.
How many vertices? The max 15, yes. The maximal number of edges for 6 vertices is indeed 16. Now, if I take each of them with a probability 1/2, on average, I should have 7.5. But of course, this is still an element of this graph because it has six vertices. And by chance, I took each of them with a probability 1/2, but it doesn't mean I can get anything. It's one realization. Yeah. If you do it many times, if you draw many graphs like this, on average, you will get 7.5 edges. This graph is one realization. One realization of an element of this set G6 1/2 or one realization. The good point with this model is that almost everything can be computed easily, or rather easily. So I'm going to state a few results because
you take different ages independent.
Yeah, I said it. The probability for edge is P, but it's independent for each of them. It's the same probability for each of them, and it will appear. So the first thing is in this set G and P, any graph with M edges. M, of course, M has to be smaller or equal to the maximal number, which is this N2. This is the maximal number of edges because it's this. You reach this number if you have edges between everybody. These are simple graphs, so we don't have loops, we don't have multiple edges. So any graph with m edges has a probability. So what is the probability to appear? So it is p power, I first write the formula, p power m times 1 minus p times n2 minus m. Can you see, and I'm going to call this p of a graph with m edge. So any graph with graph G with m edge. Can you see why we have this probability? Because we have the existence of m edges, and each of them appears with a probability p. On the other hand, we have the non-existence of all the other one, and the non-existence is given by 1 minus p, and this is all the other one, the total maximal number minus m. So this is the probability of a graph with m edge. Maybe I can emphasize this is existence of m edges. And the second factor, it is the non-existence of n2 minus m edges. But now, this is for one with this number. Now, if we want to do some statistics, so what is the distribution of graphs having m edges is given by the following thing. So the probability that a graph in this family has m edges. Remember, I have introduced this notation with a double line. It means number of edges. One line was the number of vertices. It's number of edges. It was probably in the first lecture that I introduced this notation. The number of edges of a graph, what is the probability that this number is m? It's not this number, be careful, you need to add a coefficient. It's n2 over m, and then pm, 1 minus p, n2 minus m. Where does this come from? Remember, it's combinatoric. If you want m edge,
choose and choose.
No, I guess my form, it's correct. Where does this prefactor come from? If you take m, here is 4. How many possibilities you have to put these 4 edges between these 6 vertices? And this has a name. This is a binomial distribution. Binomial distribution. And the notation for the binomial distribution is capital B, maximal number of edges, which is this n2, and the second entry is p. This is just a notation, p and over 2p. And if you look at the plot of this, you just type binomial distribution in Wikipedia, but what you have, so you have a maximal number, which is n2, and then the shape is some, maybe it's more symmetric, but it's something like this. Be careful, I put some dots because it's discrete. I consider n. So you have the probability to have 0 edge, 1 edge, no, 0 edge, 1 edge, 2 edge, 3 edge, blah, blah, blah. And if you sum all these numbers, because it has to be a probability distribution, if you sum all these, you should get 1. Okay. It's given by exactly this formula. But we can compute other things. What is the mean value for the number of edges? This is easy to guess without doing any computation. Wait a second, not only you, somebody else. What is the expected number of edges? Remember, they are all independent. So if you know something about one, it doesn't imply anything about the other one. Otherwise, it's much more complicated. Yes. So it is P times this N2, which is 1/2 N minus 1 times P. Simply because they're independent. So it's a maximal number on each of 1 multiplied by P. What is the expected degree at X? You can choose any X. It doesn't matter. It's completely symmetric with respect to all X. Can you again guess? And I'm going to give a name to this quantity. I'm going just to call it C because this C will appear later. Can you guess? You can deduce it from the previous line. Good, today. Not exactly, but there is this ID takes the previous number divided by n, but this is not exact. Something is missing. What is missing? Each edge has 2 endpoints. So you need a factor 2. 2 endpoints times the number of edges, and you divide this by the number of vertices. So it makes n times, oh no, it makes n minus 1 times p. And this relation will play a role, C n minus 1 minus p. So this is the average number of edges at each vertex, or starting at each vertex. We can already see that there is this model is going to have a problem. Our aim is to take n big, because if you want to model Google, you need to have an n big. What happens if n is big? The degree is becoming very big. And probably this is not realistic. If you think, I mean, random graph has indeed been used for modeling big networks like Google. If you have a very large number of websites, it doesn't mean that all of them are connected to most of them. This is not true. So this model is not good for some application. It's good for some, but not for all of them. And this is a weak point of this model. And we are going to change it in a second. So let me write it. Remark. Oh, you can already see, if I want to increase n, how can I deal with this? If I want to have a fixed degree, I'm going to make p also n-dependent. And then if I make it Pn dependent, I can keep this number fixed. So this is going to be an ID. So remark, a weak point of this model is precisely that this expectation of the degree grows with n. And we often prefer to keep it constant. So we prefer to have a degree which is constant. So what we are going to do, we are going to set P is, if I do this, I set P is equal to C over n minus 1. Which I can do. At the beginning, I said I studied G and P. These two numbers were independent. I'm allowed to take a P which depends on n. So this is the idea. But before, so this was a remark, we will do it very soon. Another thing which can be computed rather easily, I just give you the answer. Before we computed the mean value for the degree, but we can also get the probability that the degree at x is a certain number k. So not only the mean value, but again, the distribution. And I let you think about it, but it's the same as what we did at the beginning, n minus 1 k times k times 1 minus n minus 1 minus k. You can wonder why n minus 1, simply because if you are at one vertex, you can connect it only to n minus 1 other vertices. We don't accept loop. Maybe I should have written at the very beginning. I'm not sure I did it. We consider simple graphs. And so if you think about this, again, this is a probability of having k edges starting at one point, the absence of all the other one, and this is a normalizing factor. And again, this is a Bernoulli distribution. What we can do now, if we set P, I'm going to do what I mentioned here over n minus 1. Then we can wonder what is the limit. First year student, this is a computation for you. What is the limit when n goes to infinity of this result? But be careful, of course, I need to, it's called rescale, I need to rescale P by this quantity. So it means you just, okay, I let you write it. It's a limit when n goes to infinity of this expression, but with P is equal to C over n minus 1. And this is taking a limit. I tell you the result. It is E minus C, Ck over K factor. Of course, it should not depend on n. And what is this distribution? It's a Poisson distribution. So a limit of the Bernoulli distribution in a suitable sense, it's a Poisson distribution. And you observe that it depends only on one factor or one parameter. So it's called PC. It depends only on C. And the limit n goes to infinity, if you rescale this you get the Poisson distribution. Why I mentioned Bernoulli and Poisson, because this model is also sometimes called the Poisson model or the Bernoulli model, because we have these results. Okay, so far, I think it's not too difficult. I'm going to state two additional results, and I gave a reference for the proof. They are not so difficult, but you need to work a little bit. I state these two results just to show you that we can really compute everything. Two more results of this model. So it's a lemma for n bigger or equal to k bigger or equal to 2. What is the probability, or its upper bound, alpha of G is bigger or equal to K? What is alpha? I used it already 2 times. It's the number of vertices of the largest independent set. So remember, you have a graph. The independent set is a set of vertices where you have no connection between the point of this set. They are not linked by anything. So what is the probability that this largest number of vertices in the largest independent set is bigger than a certain k? And okay, you have to work a little bit. It's given by a certain formula. So if somebody has not done any report on if you like combinatoric, this is something for you. No. Take a graph. No. For this graph, this, okay, this, let me, I guess we have only 2, or can we have 3? No, probably we cannot have 3. This yellow set, these 2 vertices are independent because they are not directly connected. And I think 2 is a maximal number you can get. I don't think you can have 3 on this graph. So it has nothing to do with the number of components. So one combinatoric problem, but this is only an inequality. The next one is an equality. What is, it's another lemma. I'm not going to use these 2 results. I just state is to show you that we can do everything. I take k smaller than n, but bigger than 3. What is the expectation of the number of k cycles? What is k cycle? A k cycle is a cycle of length k. So you can wonder in this graph, what is the expected number on average, how many cycles you have. And again, you have a formula, and it allows me to introduce a notation. Nk 2k pk. What is this nk? I have not used it yet. I don't know if somebody has seen this notation. Oh, it's called the Pochhammer. I don't know where this guy comes from. Pochhammer symbol. And it's equal to, oh, I give you the definition. Nk is simply n. You can express it in terms of factorial, but sometimes you find it like this. So it's a product of integers n, n-1, n-2, up to n minus k plus 1. You just need to give the definition of n0. By definition, n0 is 1. These are called Pochhammer symbols, and they appear in some specific formulas. Okay, so these are, maybe I can just write expected number of cycles of length k. Again, this is some combinatoric. You need to find a way to count these cycles. If you have any question, you can ask me. Otherwise, we move to an interesting question for these graphs. When n goes to infinity, then it's about component, and in particular, the giant component. Then this is also for you. And this is also related to Ising model, if you know what it is. So I have to define what is a giant component. Because when, suppose you take n and then you put some connections, rather quickly, depending of course on P, but rather quickly you have different components. It's not most of the time so far I consider connected graph, but when you do these kind of constructions with P not too big, most probably you are going to have more than one component. So you are going to get disconnected graphs. And knowing what happens for these disconnected graphs is of interest. So for random graphs, which is something we haven't studied up to now, for random graph, one is often interested in the components of G. In particular, and of course, this is related to this, is related to C. And remember, C is the average degree. Because, or it's connected to P or to P. So it's related to C or to P, depending if you start with C or with P. Why? Because if P is 0, what happens if P is 0? It's completely disconnected. Every point is one component. And if P is 1, everybody is connected. For example, P is equal to 0 implies n components. You have n components of 1 point. And if P is equal to 1, we have 1 component. Everybody is connected. What happens in between? So in between, many things can happen. And in particular, do we have a giant component? And of course, this is of interest. We are going to study the existence of a giant component. I need to define it. But only in the limit. In the limit n goes to infinity. By the way, let's talk about philosophy. Does it exist, n going to infinity? No. Why we still study n going to infinity? Because you cannot have an infinite number of atoms, so n going to infinity cannot exist. Still, often it becomes simpler when you take a limit. Things become simpler when you take, or when you can take a limit n going to infinity.
You can't have n going to infinity if the graph connects back to itself.
It's just, you can wonder in mathematics why we consider limits going to infinity, but simply because things are often becoming simpler. So this is why we take graph going to infinity. So what is a giant component? Of course, if I give you directly a graph of size infinity, it's difficult to define it. So how we do it, think like this. You increase the size of your graph. So or you start with an infinite graph, but you cut a part, and then you cut a bigger part on a bigger part. So the definition I'm going to write is, we consider an increasing sequence of finite graph, but of course, this sequence has to go to infinity. So this is how I'm going to define a giant component, by looking at subgraph. And what is, you can already guess. So I'm going to increase, this is Gn, it's going to be a family Gn. A giant component, by definition, it has to be, or to become, bigger and bigger. Okay, so now if you have this in mind, the next definition will be clear. Definition. So a family of graphs. And I call this family Gn. N is an integer. Satisfying the number of, remember the number of vertices is given by this single, these two single lines. So I want this to go to infinity when n goes to infinity, so they are really growing. This family possesses a giant component. If there exists a sequence of subset Gn, is subset lambda n are the yellow one. So there exists a family or subset, a subset in Gn. Connected graph. So the yellow part has to be connected, a connected graph. But it's not enough. There also exists an epsilon bigger than 0. We will understand why, such that the size of lambda n is bigger or equal to epsilon times the size of Gn. Can you guess why we impose this second condition, or the existence of this epsilon? Maybe I put a strictly bigger, but this doesn't.
0?
No.
What do you want epsilon smaller than 1?
Yeah, epsilon is always small. Of course, it's smaller than 1. Yeah. But why? Think about this. I don't want to have a line in R2. If you think about the big graph as R2, one line could be, depending on the definition, but it could be a giant component because it has also infinite number of vertices. But you have this idea that it's too small. So by imposing this, it means if these grow with a certain speed, or with I mean, if you think about a square growing in R2, you can see how many points you have when it grows. You want the size of the giant component to be of same size. So we want to avoid to have just one line in R2 or in Z2. So this is this condition. Oh, let me write just. Wait a second. So remark about this second condition, remark. If Gn, how can I, okay, it is, let's say, minus n minus 1 up to n minus plus 1. I'm not sure it's the best notation, square. So this is Gn, a square. Maybe I should not put this notation. It is the set square. Please make the picture in order to understand this notation. If I want to consider these points from minus n in 2 dimensions, okay, then the set, okay, no, sorry, I have a better notation. The set of point jk, that's better. The set of point jk, j and k belonging to minus n up to n. That's better. This is Gn. The set of points in R2, which are integer between minus n and n. Okay. Then what I don't want as a giant component, then the set 0 j for any j between minus n and n is not a giant component. It's too small. Okay, this is what I wanted to say. On the other hand, if you take, let's say, a quarter of this, and this, if this is your lambda n, then when it grows, it's going to be a giant component. So this is the idea behind this condition. The growth of this part should be comparable. The ratio of this size by the other one should not become too small. Okay. So this is a definition of a giant component. It's something growing at the same speed as the family of graph. So we want to compute the probability of existence of such a giant component. So the existence of the giant component depends on P. What I didn't, okay. If all, oh, I have a clash of notation, but okay, please accept it, belong to G and P. So what I have in, no, it's still fine. I'm in this setting of random graphs, which means all the subgraph I consider are constructed with this, still the same rule. Each edge is independent from the other one and exists with a probability P. That's the only thing. Okay. So we are going to compute something about this giant component, and surprisingly we can. So assume it exists. What is it? It's this giant component. Assume this giant component exists, and I'm going to define U be the probability that an arbitrary vertex belong or does not belong, does not belong to it. So I'm in this setting, I assume that we have a giant component with the definition I had given, and I define U as the probability that an arbitrary vertex belong to it, does not belong to it. I need to also assume one thing, but we will not see it, but implicitly we use it. Assume also that this lambda n over Gn is a constant. So before it was bigger than epsilon. If you look carefully in the proof, you need to assume that it's constant, but this is not a big issue. So take X not belonging to the giant component. So Gn minus this lambda n. So I take a X here. This is my X. And I consider another point, Y, which belongs just to Gn. I don't know if it is in the giant component or not. Okay, so I have a Y somewhere else. Y is here. The probability that X is connected to Y, we know it, is not connected. Probability that X is not connected to Y is 1 minus P. So that X not is 1 minus P. This is known in our model. Not being connected is by 1 minus P. If X is connected to Y, which has a probability P, because the complicated sentence is the following one. If X is connected to Y, then what can I say about Y? Does Y belong to the giant component or not? No. Because if Y belongs to the giant component, then X also belongs to it. And I assume that X is not. So if X is connected to Y, then Y cannot, or is not in the giant component. Because otherwise, X is also otherwise. X would belong to it. Okay, so if we have this in mind, then I can continue my computation. So what does it imply? The probability that X does not belong to the giant component through Y, through the vertex Y is equal to either 1 minus P. If they are not connected, of course, it cannot connect it to the giant component, plus P times U. Y plus P times U, because it is plus the probability that P is connected to Y, but Y is not in the giant component. So think about this. But now, since Y is arbitrary, we get is arbitrary among n minus 1 vertices. Yeah, I'm not completely precise. No, I am now. The n is really referred to the number of vertices. So I should have mentioned when Gn has really n vertices. And this, so when I said Gn is an element of Gn, it was correct. N minus 1 because it cannot be X itself. So what it implies? It implies that U, the probability of not being in the giant component is equal to probability of X not in lambda n, but it's equal to this 1 minus P plus PU, everything power n minus 1. Because everything, all points or all edges between X and Y are independent. And if you just do a small computation, this is, I'm using now that C is going to be, oh no, yes, C is n minus 1 times P. This is what we had before. Why I need to rescale? Because as we have seen, we need to keep C and not N. So if I use this, I get 1 minus C. Now you are going to recognize something. What is this expression when N goes to infinity? So it's just a small computation. You factor P and then you replace P by C over N minus 1. That's nothing. What happens when N goes to infinity? Yes, it's going to an exponential. So this take a limit when N goes to infinity, it goes to E minus C 1 minus U.
U equals probability X not in sigma n. Is that a bar?
So by definition, U is P of probability that X is not in the giant component. And now, as I said, it's the probability that it's not going in the giant component through Y, but Y is arbitrary among all possible vertices, and the existence of an edge, they are all independent, so I get this. No, it's correct.
I thought that the bar meant that Y is also not connected. And you were going to write another condition.
No, because this is by definition, and now I take the fact, if this is a parenthesis, or you write it through Y for all Y, and then you get the next line. So we end up with the equation U is equal to E minus C 1 minus U or if I set S is 1 minus U, this is equivalent to the equation S is 1 minus E minus CS. You have probably already seen these kind of equations. You cannot solve them, but you can still do pictures. And this is very useful. So what is the meaning of S? By the way, S is the probability of that X belongs to the giant component, because it's 1 minus not belonging. So how you solve this kind of equation numerically? The left-hand side, you plot this function, so the variable is S. So this function is a function S, identity. And the other one, how it is, depending on C. If C is, I'm going to do 3 cases. It should not decay. What is the maximal value? X1. This is 1. What is the yellow case? The yellow case is when it's tangent at the origin. You get it when C is equal to 1. When C is equal to 1, you can check the derivative is also 1 at 0. The other case is when C is smaller than 1, and the blue case is when C is bigger than 1. So let's look at this. It means when C is bigger than 1, we have one solution of this equation. So it means we have the existence of a giant component. And what is the probability of this giant component? It's given by the value of the intersection, or 1 minus the value, no, by the value here. So this value here, which can be also seen here, is S, but in fact it is S for a certain C. It is a probability that X belongs to a giant component. So this is the probability of the existence of the giant component. No, it's a probability that if you pick a X arbitrary, you are in the giant component. So the intersection of the two curves gives the solution. And what we observe for C bigger than 1, there is a non-zero probability to be in the giant component, So it means it exists. For C smaller than 1, it doesn't exist. There is no solution. For C bigger than 1, there is a non-zero probability to be in the giant component. For C smaller or equal to 1, the equality C equal to 1, you need to do a little bit, you need to go a little bit further in the analysis. For C strictly smaller than 1, there is no giant component, because the probability to be in it is 0. So it means C is called a phase transition. It's called a phase transition. There is one small result. I'll explain how you get it in the notes, but let me just say it orally. You can wonder, oh, for C bigger than 1, can we have more than one giant component? Can we have big graph? Can we have 2 giant components? And in fact, you can show that the probability of having 2 is 0, because they will certainly connect at one point, and then it's only 1. So one can show. Yes. In the limit n goes to infinity and C bigger than 1, the giant component is unique. Because if you have 2, the probability that they touch is 1. This is just a small remark. Okay, so we have only one giant component. Still, it doesn't cover everything, because let's take still another value, a slightly smaller value. Oh, I have no other color. Okay, let's take a value like this. You have the probability here to be in the giant component, but it means you have also a probability not to be in the giant component. So what happens here? Here you have plenty of connected graph. Small. But if n is going to infinity, you have plenty of them. And they cannot be all connected because they would belong to the giant component. So we can also study these guys. They are called the small components. Small components can also be studied. And it's quite interesting, can also be studied. So I'm going to state a few results about them. Let me just keep this for a second. So the first one, it's a little bit surprising. Let GS be a small component of S vertices. So one component of S vertices. The first result is that the probability that GS is a tree. So I take, let's say, four vertices. What is the probability that this small thing is a tree? So you have no cycle. Can you guess?
1 minus probability that there is a cycle.
Okay, this would be easy. In fact, it's 1. It means that most, with a probability 1, if you pick one small component, it's a tree. It costs a lot of something, a lot of energy to build a cycle. There is an argument in the notes. It's not completely clear. You need to think about it for a while. But yeah, most of the time, or with a probability 1, you have only trees. Of course, you may have a cycle, but among all of them, it's of probability 0. So this is the first result in the limit n going to infinity. So when you consider. Then the second, I just give you the answer. X is in the component of size S. So what is, you take a X arbitrary, either here or here, but here it is in the giant component. But take a X in this part, what is the probability that the X belongs to a component of size S? Okay, I cannot show you the result, I mean, how we get it, but there is a formula. Just wanted to tell you that everything is computable. So this is the probability that if you pick a X anywhere, it is in a component of size S. And the third thing that I give you, what is the expectation of the size of Gx for X chosen randomly? So we have to be very careful about the statement, what it is. Now, okay, I computed the probability of being in one of size S. And now what is the average size of these components? So what is the average number of vertices for X belonging to this guy chosen randomly? So again, you pick first X, you count the number of vertices of this component. Then you take a second guy, you count, and then you do the average. It turned out that this can also be computed. It is 1 over. Oh, yes, maybe what is the S in this formula? It is the S that you read here. So it's a solution of this equation for given C. S is a solution of this. It is a number that you have here, the intersection. So it can be computed. And quite surprisingly, or not surprisingly, you can see that this guy has a singularity as singular at C is equal to 1. So it means average, or the expectation value of this average, the expectation value of the component where you find randomly an X has a singularity. And you can try to understand this. Of course, it takes some time, but okay. No, it's correct. What happens when C is equal to 1? Formally, you have 0, but C, the intersection is S is also 0. And you can do a plot. In fact, you can approach either by below or by above, or C going to 1. And you can see that you have a singularity both from below and from above. And you can try to understand it, but it takes some time. So what we should remember, we have developed a certain model, this model of random graph, and you can check when the size is going to infinity, what happens with the existence of a giant component, but also what happens with the small components. And if this model is going to represent something, of course, there is an interest in studying what happens in some limiting case. I want to move to another coefficient which plays a role in this business is the clustering coefficient. You can relate this to the famous sentence, friends of my friends are my friends. My friends are or are not my friends. And we will see why. But this is important. This property is used precisely in many applications. So what does it mean? This clustering coefficient is going to measure, I will give a definition, but it measures if vertices in a graph tend to cluster. So if they tend to be tightly connected or not. So what is going to be a precise definition? It's defined with triangles. So there are two definitions, the global definition, and there is a local one, global definition. This cluster coefficient or clustering coefficient numbers. Can you understand this definition?
The bottom before the graph.
Number. Okay, it was not my. Okay, number. Look at your complicated graph. No matter what is your graph. This definition is independent of the model we consider. You look at all triplets of vertices, and you count how many times you have a closed triangle, and you divide by the total number of things where you have three vertices, but connected only by two edges. Okay. This is called closed triplets divided by open triplets. Or you can do a local definition because this is global, but sometimes we want to know around a certain X, what is a clustering at X. So I define Cx. Again, it's a ratio. It's a number of closed triplets, but with one vertex X divided by a certain number, 1/2 of X time. Why this denominator? Because look, when you have an X with a certain number, a certain degree, the number of triangle you can generate possibly is given by this number.
That's the order of the line.
Sorry?
Yeah.
No, this is if this X has a degree, you can compute the number of triangle and it's given by this. And so these definitions are valid. I mean, you can define them for any graph. And of course, if you have this locally, you can compute its average. You can also define C bar, which is 1 over the number of elements of G times the sum X Cx. And you can wonder or observe that in general, this is not equal to C. Oh, this is just an observation. You can define the average of the C of X by this formula. In general, these two numbers do not coincide. This is just an observation. Now, what happens for our G inside C or G and P? What are these quantities in general? So these quantities are defined for any graph. Now we need to take expectation because we have families. So what is the expectation of C and what is the expectation of Cx for graph in our family? In fact, it turned out that for both it's P. Can we see it? You have to take into account that, yes, having this additional edge is independent of the other one. So having one more compared to this one, it has a probability P. That's it. And in fact, this is the same here. So you use the independent, and this is important, this is part of the model. You use the independence of all edges and you obtain this. Okay, so yeah. If we summarize what it's a section, it's the last section, which I call weaknesses. Weak. It doesn't mean this is not a good model. It's a good model in the sense we can compute everything. It has certainly been used for certain models, but it cannot apply for everything, of course. So the first thing we have seen is the deg of X is becoming too big, or is too big if we keep E constant. But of course, we have seen that we can rescale and we can do something for this problem. But this is one weakness of the other of this graph. Now, what happens if I rescale? Remember, what was the relation between P and N? It was, what was it? P was C over N minus 1. If now I rescale like I did before, what happens? Then this guy is becoming too small. So if about the cluster, the cluster coefficient are becoming or are too small, if we set T is equal to C over N minus 1. So what we saved by taking this rescaling, we lose it in the sense that now the clustering coefficients are very small. And in many applications, it's not true because the friends of my friends are really my friends. In many applications, whenever you have the connection between one person and this person is connected to a second one, there is a high chance that there is an additional connection. So you don't want, in application, you don't want to have a clustering coefficient which becomes so small. So this, and in the notes, I put a table of some graphs which have been studied, and you can see there is this clustering coefficient has been computed on some real applications, and these are not becoming so small. So this clustering coefficient with such a formula is becoming too small. So that's one weakness. And the last weakness is about the distribution, or the degree distribution. We have seen for large N, the degree of X has a Poisson distribution. This is something I mentioned. But the Poisson distribution has an exponential decay. If you look at the Poisson distribution, this is exponential decay. And again, in applications, often it's not decaying so fast. In applications. One has often that the degree of X equal to K. So the probability of this, when K is large, we don't want exponential decay. We would like to have something of the form 1 over K power P, or which letter? Power alpha. Which is, it's called a power law. And it decays less, so power law decay less fast. It's not as fast as an exponential decay. So it means in application, we often don't want to have such a fast decay. We would like to have something which decay at a slower speed. So we have to develop some model for this. So our next task is to develop other models which either have a better decay or a better behavior with respect to the clustering coefficient. And for sure, we don't want a degree which becomes so big. And there is another thing which you can feel. Space has not been used today. I mean, these points are just located arbitrarily. You can put them on a circle and do the connection arbitrarily. But in fact, for many models, space, if you think about people and connection between people, the distance plays a role. So we have to implement these kind of ideas. Okay, do you have any question? It's rare that I finish 5 minutes early. Yes.
Does there exist a giant, there's an infinite component which is not a giant?
Yes, the line into R2. But so take Z2 on the line Z. It's an infinite component, but it's not considered as a giant component because it's too thin. Yeah, the ratio, and you know it from the measure of a curve into R2. A curve has no measure in R2 because it's too small. So this is the same thing. You want something which has the ratio between the size of the big space and the other one should not be 0. So yes, you can have a set of infinite size because it's still of infinite size, but which is not a giant component in the definition I gave for giant component. Maybe this is useful for other applications, but not for what we do.
Families of sets that we consider when we are looking for the giant components.
Yes.
Can we split them into ones that?
Okay, so there is a question about family. So we discussed GN, the family GN converging or going to infinity in a certain sense. If you want to do things much more precisely than what I have done, indeed, you cannot consider arbitrary sets. You have to be a little bit more careful. Boxes are perfect, but cauliflowers are not good. You remember, I already have this, I already mentioned this at some courses. When you consider sets, a box is good because, or a circle is good because the ratio between the surface and the volume is understandable. Now, if you start with sets which are like this, and more complicated, whatever, this is what I call a cauliflower. If you try to develop your theory with such things, you probably have problems. But, you know, I cannot give you the exact proof of what you do if you really want to study this. You have to be a little bit more careful. So yes, the size of, or I think there is a name for the ratio. It's called a Fellner sequence. You can check. Fellner sequence is precisely a sequence of sets such that you control the ratio between the surface and the volume. So you have, yeah, the Hausdorff measure, but it's related to this. But there is a more general concept of Fellner sequence. So yeah, you have always to be more careful. You know, I give the lecture at a level 1. You can go up to PhD in this kind of subjects. I cannot do it here. And when I mentioned the proof about the giant component, I also said this has to be equal to epsilon. But if you look on what I presented, I didn't use it. It's because when you do the thing a little bit more carefully, when you take the limit carefully, indeed, these kind of assumptions come into account, appear. In what I've presented, it doesn't. But I just want the, you know, the problem, what would be the problem is if this ratio, for example, oscillate when n goes to infinity, or yeah,
That's also very interesting.
everything is interesting. As long as you study it carefully and with pleasure, it's interesting. Okay, any other question or remark? If not, it's time. So I expect to have between 2 and 3 more lectures. I don't know what is the meaning of between 2 and 3. At least 2, this is sure. I don't know if we can cover everything within 2 lectures or if we will have 2.5 or something like this. But independently of this, please don't remember to submit reports. I haven't seen reports for a while from some students. Okay, thank you. And if the same for you, if you have any question, you can either ask now or later by email.